Hi, I'm Alistair. I'm an interactive game designer and electronic engineer, and in this video I'm going to compare various commonly available audio modules that you can use to add sound to your electronics projects, either using a microprocessor such as an Arduino, ESP32 or Raspberry Pi, or just as a standalone device. Now let's start by looking at this. This is a DF Player Mini MP3 module. Now, loads of electronics projects on the internet, including many of my previous projects on this channel, use these modules. They first became available about 5 years ago, I think, and there's lots of reasons to like them. You copy songs or sound effects onto an SD card in a WAV or MP3 format, and then it can operate in several different modes. If you want it to act like an MP3 player, you can use pins on the side of the board to start or stop playback, change track or adjust volume. Or if you want to use it as a soundboard, you can connect different resistor values to 2 of these pins to trigger up to 14 different tracks directly. Or you can create a serial connection to a microprocessor like an Arduino and send serial commands that allow you complete programmatic control over all of its features through code. The board has got stereo DAC output and even has a small onboard amplifier chip, so you can connect a small speaker directly to it. But it should be said that these are not quite plug and play devices. Even though you'll find examples on the internet where people just plug in 5-volt power or wire directly to the GPI pins on an Arduino, that's not correct. And even though it might seem to work, it can lead to a lot of problems further down the line and waste time having to debug problems with noisy audio or songs cutting out after a few seconds or other weird behaviour. It might also damage the board in the long term. So let me quickly summarise the steps you need to use these boards properly.
So the specifications say that the DF Player Mini needs to be powered with a voltage somewhere between 3.3 volts and 5 volts at the V-in pin here. But if you were to connect this directly to the 5-volt pin on an Arduino, say, you'd be right at the top end of that allowed voltage, and you'll probably encounter some noise and stability problems. You really want to drop that voltage down slightly. And a common way to do that is to place a diode in series in that voltage line here. A diode typically drops about 0.7 or 0.8 volts across it. So you've got the voltage being supplied at the first pin here now about 4.2 volts, and that's an ideal value. Now, as well as specifying the correct voltage, you also need to make sure you can supply sufficient current. The audio chip itself draws about 150 milliamps. Accessing files on the SD card can require up to about 100 milliamps, and if you were to turn the 3-watt amplifier up to maximum, that would draw another 600 milliamps at 5 volts. So the board can draw almost 1 amp of current at its peak, and that far exceeds what you can draw from the 5-volt regulator on an Arduino. So you really need to be using an external power supply to supply this 5-volt source here. And ideally you also want to have a capacitor close to the board which is going to stabilise that power supply. So I typically use an electrolytic capacitor like this, and you need to place that close to the board and with the positive leg connected to the V-in pin and with the negative leg connected to one of the ground-in pins. That's going to help smooth out any sudden current inrush that is demanded when the Mini first turns on or when you first start playing a track. Now you'll see that there are 2 ground pins on the board here. I've got this one over this side that I've just connected the capacitor to, and there's another one over this side. And yes, you do really need to connect them both to ground. These boards are tiny, but that means that analog audio signals and the noisy digital components on the circuit have been crammed together, very close together. There's no isolation or filtering between them. So providing a good ground connection will help reduce issues with static or noise on the audio output. And then, irrespective of the voltage that's being supplied on the VCC pin here, which we said is now about 4.2 volts, the logic level used on the interface pins is always 3.3 volts. So if you are connecting this to an Arduino, we've got the receive pin here, and we have the transmit pin, which sends messages back to the microprocessor here. So if you want to trigger playback from the GPIO pins of a 5-volt Arduino, you're going to need a logic level converter, or at the very least a 1 kilo ohm series resistor on this line here, which is the line that is going to have a 5-volt signal sent from a GPIO pin of an Arduino here. This will just limit the current that is being received at the receive pin here, and this will protect the circuitry of the DF Player Mini. There's no need to place an equivalent resistor on the transmit line going from the DF Player to the Arduino. That will be at 3.3 volts, and that will be perfectly good to be read as a logic level high on an Arduino. Now, if you're using a microprocessor that natively runs at 3.3 volt logic, like a Raspberry Pi or an ESP chip, you don't need to put that resistor in the receive line there. It's only necessary if you're using a 5-volt microprocessor like an Arduino Uno or Nano that drives its GPIO pins to 5 volts high, and you need to drop them down to an acceptable level for the DF Player Mini, either using that series resistor or through a dedicated logic level converter or through a resistor divider circuit. But you mustn't ever drive it directly at 5 volts. So here is a complete wiring diagram of how you should connect a DF Player Mini module to an Arduino. And as you'll see, it's a little bit more complex than some examples you might have seen on the internet, but this actually ensures that you're operating within the specifications that are published for the device, and also you'll probably eliminate a lot of problems that people sometimes encounter with using these boards.
Now, as an alternative to the DF Player, there's also boards like this one, which I've also used in projects on this channel. It's often marketed as a Catalex serial MP3 player board, and it's got lots of similarities to the DF Player. The main differences are that it doesn't have an onboard amplifier. Instead, it's got this 3.5mm jack socket, so you can connect headphones or you can use an audio cable to take that signal out to an external amplifier. It also doesn't have any I/O pins, so you can't use this as a standalone device. The only way you can control playback of audio from the SD card here is through the serial interface from a microprocessor like an Arduino or Raspberry Pi. Now, the commands that the chip understands are exactly the same as used by the DF Player, so you can use the same Arduino libraries to control either of these devices. It's also a little bit more tolerant and easier to use than the DF Player. It already has a built-in resistor on the receive signal, and it has some capacitors on the power supply lines. So those external components that I said had to be added to the DF Player are already on this board. You can wire this straight up to an Arduino 5-volt power and ground and 2 GPIO pins for the transmit and receive signals, and it will work great. Now, the reason why the DF Player and the Catalex board are so similar is because they're actually based around exactly the same audio processor chip. Or at least they should be based around the same chip. And that brings me on to the biggest problem I've encountered with either of these boards. And to demonstrate that, I'm going to show you them under my microscope. So we'll begin with one of these serial MP3 player modules, and we'll take a closer look at it. So here we've got the interface, the 4-pin interface, and we'll see that the receive line goes via this built-in 1 kilo ohm resistor, as I mentioned. And if we follow the VCC line here, we'll see the trace comes down the board across through these 2 ceramic capacitors. This one's been slightly shonkily soldered on, but that will still work. And these are going to help smooth the power supply out. Remember that this board doesn't actually have the onboard amplifier, so it's less demanding in terms of power than the DF player anyway. And if we carry on following that trace up, we get to the audio clip itself. You can see this is clearly labelled. It's a YX6300 clip. Now let's take a look at another of these boards there. This is apparently the same board. I just bought it from a different supplier on Amazon. And if we start here, okay, so once again we've got the receive line going through the built-in series resistor. We've got the VCC line that goes down through the two capacitors, but this time we've got a completely different audio chip on the board. It's made by a different manufacturer, it's got a different model number. Even though it seems to have exactly the same pin out, it's still got exactly the same connections to the other components on the board, and if you were to try to use these two modules, you might not have noticed any difference between them at all, but they're clearly not the same. Now let's take a look at one of the DF player modules. Now this has got a slightly different board layout. So the chip on the board here, this is actually the amplifier chip, but this is the audio chip, and according to the schematics, this should have been exactly the same as in the previous two boards. But again, we've got a completely different manufacturer and model number. And I've got another DF player module here. And this is perhaps the worst of the bunch, because whatever markings there should have been on this chip appear to have been scratched off. Now, we don't know the reasons for that, but it seems likely that this is some sort of counterfeit chip and the seller is trying to avoid traceability or trademark issues by marking off any possible identifying marks that would have been on the chip. Now the problem is it's almost impossible to tell which, if any, of these modules use genuine chips. When I started researching this video, I thought that the YX6300, the first chip I showed you, was the original. It appears to be made by a company called Flyrun Tech, and they're a company that creates a variety of embedded audio devices based around chips with the YX prefix. But on their website, they state that it's their YX5W chip that's used in the DF Player Mini, and none of the modules I just looked at have used that chip. Now, is the YX6300 simply an upgraded version of the YX5W, or has it just been named similarly to that by a different manufacturer to make you think that you're buying a genuine product? I don't know. And does it even matter? Well, yes and no. I'm not even going to go into the morals of buying counterfeit chips. The problem from a technical point of view is that even though these different chips behave in pretty much the same way for the vast majority of functions, they're not completely comparable. They don't all produce the same audio quality. Some produce noticeably more static or hum, or they introduce a longer delay before playback, or you can hear high frequency clicks when the SD card is accessed. And there are also some more advanced features like navigating to a particular folder or playing a specific track by its file name that are simply not implemented on certain chips. And there's no way of knowing when you buy one of these boards which chip it will use. That's not always a question of where you buy it from either. I've got these from a variety of sources, some from Amazon and eBay and AliExpress, but others from more reputable sources like RS Components and DiddlyKey. So you just don't know. And if you're using a library that someone else has developed, or even a project that you yourself wrote that used one version of this, there's no guarantee it's going to continue to work the same way in the future. Now, that's not to say that these are of no use. They are, after all, incredibly cheap, and I've got a drawer full of hundreds of them. So I'll probably be continuing to use them for some time myself. But I don't necessarily think I'd recommend them as the go-to board for new projects. And I think that there are now better alternatives available. So let me introduce you to some of my current preferred audio modules, which are based on the DY series of audio chips. This is the DY-SV17F, and it's the most basic board in the DY family. So it's a compact module, slightly bigger than the DF player, and like the DF player, it has an audio decoder chip together with an integrated amplifier that can be triggered either by a serial connection or used standalone using the I/O pins on the side of the board. Also, like the DF player, it can provide audio output either via speaker pins or via a DAC output. Now, one key difference compared to the DF player is that instead of having an SD card reader, you store the audio files on an onboard 4 megabyte flash memory chip. Now, that's actually really easy to do. There's a micro USB socket at the base, and when you plug a USB cable from your PC into that socket, it gets recognised as a USB storage device, and you can just drag your WAV or MP3 files onto the board. You don't need to install any funky drivers or anything like that. Other improvements over the DF player is that it's got a few equaliser settings that alter the sound quality, and the amplifier is rated at 5 watts compared to the DF player's 3 watts. But like the DF player, one of the consequences of this board being so compact is that it still requires a few additional external components to use it.
So this is how you'd wire the SV17F to an Arduino, and you'll see there are some similarities to the wiring I showed you for the DF Player Mini, and there's also some important differences. So first of all, in terms of the power supply, notice that we no longer need to have the external capacitor across the VCC and ground lines, because there are built-in capacitors on the board here that are capable of smoothing the power supply on the internal circuitry. And we also don't need to have that diode in series to drop the voltage down slightly. We can supply VCC at exactly 5 volts into the V-in pin here, and that will work just fine. However, note that the logic level that is used for all the internal logic is 3.3 volts still, just as it was with the DF player. And that means if you're going to interface it with an external device running at 5 volts, like an Arduino, you do need to drop any signals that are going to be received as high signals on these pins. So the pin here, this is the receive pin, and if we're going to use a serial interface from a 5 volt Arduino, you need to place a kilo ohm resistor on that line before the pin. Or you could use a resistor divider circuit or a dedicated logic level converter to drop that signal line down to an acceptable limit at this pin here. Again, there's no need to place a resistor on the line here. This is the transmit signal from the SV17F back to the Arduino. That doesn't need to be stepped up at all. And if you're using a 3.3 volt logic device like an ESP32, you don't need to have that resistor in place either. Now, I did also mention that the SV17F has different operating modes, just as the DF player did. And these are selected by using these 3 CON switches here. Now, by setting these to a combination of high and low values, you can choose between the different operating modes. But annoyingly, they don't have any built-in pull-up or pull-down default values. So you do need to explicitly pull them high or low. And that either means pulling them up to 3.3 volts or down to ground via 10 kilo ohm resistors in either case. And these are not available on the board, so you do have to provide these externally. Now, there is a 3.3 volt output pin on the board, fortunately, makes it a little bit easier to wire that together, but it's still a bit of a pain. In terms of the different operating modes, how they operate, so if these were all pulled down to ground, that would play a momentary song indexed by the pattern of input keys that you press on this side of the board. So if you were to just ground the top pin, that would play track number 1. If you were to just ground the second pin, that would play track number 2. But to play the third track, rather than pressing the third pin along, you press 1 and 2 together, because it kind of treats it as a binary pattern. If you wanted to play the 5th song, you would press just the first pin and the third pin, because that would be the binary values 1 add 4 to make the 5th track. So with any pattern of the input pins on this side of the board, when you are in low, low, low mode, you can play up to 255 different audio tracks. Now there is also a latched version of that as well, and that's if you set the pins to low, low, high. So in the low, low, low version, the song will only continue playing for as long as you hold down that pattern of input keys. When you set it to the low, low, high latched version, you simply press that input pattern once and the song will continue playing through to the end or until the next track is triggered. Now there's another way of indexing files instead, and you get that mode by setting the pins to low, high, low. So connect this pin to ground, this one to 3.3 volts via a 10 kilo ohm resistor, and this one to ground again. And in this version, the tracks are numbered probably a bit more logically. You simply have 8 trigger pins here, and they correspond to playing tracks 1, 2, 3, 4, 5, 6, 7, and 8. So a single button, and you could wire that to a switch or to some sensor or any actuator at all. When that pin is grounded, the track will play. And again, there's a momentary and a latched version. So low, high, low will allow you to momentarily play any of the first 8 numbered songs on the card, and low, high, high would be the latched version of that, where pressing that button once started the song to play and it would play through till the end or until another track was started. And then we've got 2 more advanced modes of playback. We've got the one which I'm demonstrating here, so this is high, low, low, and this is the serial interface mode. And in this mode, this is where we're going to send commands from our microprocessor here through the transmit and receive lines. And there's also an MP3 player mode, and this acts similarly to the DF player MP3 mode, where the buttons correspond to play, pause, advance track, and return to the previous track. So it's a little frustrating that this board is not quite plug and play. You still need to use some additional components to make it work, and combined with the fact that the 4 megabytes of onboard memory is pretty limited, perhaps means that you want to look at the next more powerful boards available in the DY family of chips. And there are 2 of those. They are the DY-SV5W and the DY-SV8F. So these are both upgraded versions that come with a substantially larger footprint, and one of the reasons for that is that they now contain all those additional components on the board. So instead of having to connect any external resistors, you can now use the dip switches at the top here to select between different playback modes. And you'll see it also adds a 3.5mm jack output if you want to use that instead of the speaker out. So if you want something that is ready to plug directly into an Arduino or ESP32, that's a great improvement. Now the difference between the 8F and the 5W boards is that the 8F has a flash memory chip, like the SV17F did, while the 5W has an SD card slot, like the DF Player Mini. So when you come to choose between those 2 units, the obvious decisions are things like speed of access versus storage capacity. This is actually an upgraded amount of flash memory, so it's 8 megabytes on here, twice that of the SV17F, and that's sufficient to hold a couple of minutes of high quality MP3 data. And that might be enough, but on the SD card version you can use SD cards up to 32 gigabytes in capacity, which is 4,000 times more storage. But flash memory is faster than an SD card, or at least it should be, which means that playback should be more responsive from the flash memory version. There's less of a delay after receiving a trigger before the sound playback starts. Now in terms of how much faster, that's kind of hard to say. SD cards are rated in different classes, but that's based on their write speed. The important factor in creating a responsive sound player is the latency when performing a random read operation from the card, and that's not something that SD card manufacturers generally advertise. So I set up a little empirical test to test the 2 versions out. So in a not very rigorous scientific test environment, here I've got one of the flash memory based DY players, and here I've got one of the SD card based players. And they are both connected to these push buttons, and I've got the dip switches set so that they will trigger the first sound effect saved when those buttons are pressed.
Now I've got exactly the same MP3 file saved onto both devices, and what I'm now going to do is simply press these two triggers simultaneously and play you what happens. Now, I hope it was able to come out clearly on the video there, but there's a significant lag between them. I'm going to do it one more time. And I appreciate this probably wouldn't come out in the video. What I was totally expecting was for the SD card version to be lagging behind the flash memory version. Flash memory is generally faster to access than the SD card. But actually I was really surprised to find it's not. It's the other way around. I can try to demonstrate that to you. So this is the button that's connected to the flash memory version, and what I'm going to try and demonstrate is if I press this one and then about 1/10 of a second later I'm going to start off the SD card one and see if I can get them to be in sync with each other. I hope you're able to hear the difference there. So there's actually about 1/10 of a second between them, and I genuinely can't explain the reason why that would be the case, because I really thought the SD card would be slower. Just for reference, I am using a SanDisk branded class 10 SD card here. So this is a good quality SD card, and it is possible that if I was to repeat this experiment with a cheaper non-branded SD card, that this would be slower. But based on my test at least, there's actually slightly improved performance on the SD card version. So in all honesty, if I were to recommend one of these boards, I would probably go for the SD card version, which is going to mean that you can include more sound files, you can include full-length songs or ambient music loops. But maybe there are other scenarios when the flash memory version is more suitable. If you can think of any, please do let me know. Now, I can't really make a tutorial about audio modules without answering the question about how loud they are. So in terms of volume, both the 5W and the 8F boards have the same 5-watt Class D amplifier on them, which can drive 4 ohm impedance speakers up to 5 watts. And that's plenty loud enough for most applications. It's also perfectly clear enough to hear speech. But if you want something that's going to be louder than that, perhaps an explosion or other sound effect, then you can step up to the next two modules in the DY series. And these are the DY-HV20T and the DY-HV8F. So these are upgraded versions of the two previous boards. The DY-HV8F has an 8MB flash chip, whereas the 20T has the SD card reader. And the difference compared to the previous family boards is that instead of being powered at 5 volts, you power them with a DC input between 6 volts and 35 volts. And in return, instead of having a 5-watt amplifier on board, you get a 20-watt Class D amplifier. So that's equivalent to you might get from an electric guitar amplifier, for example.
I think I've said pretty much all I can about the hardware side of these modules, so now let me say a little bit about the software I use and how to prepare audio files for playback. So I use Audacity. It's a fantastic piece of free open source software, and it has pretty much all the audio editing features you could possibly need. You can use it either to edit existing audio files, or you can connect a microphone and make a new recording. And some of the things you'll want to do is to select your track and to normalize it. This is going to adjust the volume so that it maximizes the complete dynamic range while not clipping at the top end here. It basically stretches the volume to be as loud as possible while not distorting. And another thing you might want to do is to trim off any silence that might be at the beginning of the track. And you can do lots of other effects and all sorts of changes to your file here as well. And once you're happy with the edits you've made, what you need to do is go to the File menu and export it either as an MP3 or a WAV file. Now you can export these up to 24-bit at 48 kilohertz, so that's better than CD audio quality. And whether you're using the flash version or the SD card version, what they will do is they will appear in your file explorer here just as another drive that you can save to. Now the important thing to note is the rules on how you name your file, and this is true for these boards that use the DY chip as well as the DF Player Mini, the Catalex, or the Arduino sound boards. In fact, every embedded audio module I've ever used uses these same rules. So to explain the next bit, consider first of all what happens when you play an audio track on your computer in iTunes or whatever. You double click the file name and the operating system queries the underlying file system to access the relevant sectors of data from the hard disk corresponding to that file. But these simple embedded audio devices don't have an operating system. They have a very primitive way of identifying each file, which is simply by an index number. So when you save audio files to Playback on any of these audio modules, you need to give them numbered file names like 00001.mp3, 00002.mp3. But here's the thing, the module isn't actually accessing by that number. It's indexing them by the order in which they were added to the file allocation table. So if you start off with a blank disk, a blank SD card, or an empty flash memory chip, and you save the file 00001.mp3, it will be assigned the index 1. And that's the file that will play when you press the first button in trigger mode, or where you issue a serial command to play back the first file. If you then copy over a file called 00004.mp3, it won't be assigned the index 4, it will be assigned the index 2, because it's a second file on the disk, whatever the file name is. So the reason for giving the files sequentially numbered file names is just that, generally speaking, that's the order that Windows or OS X will copy them across when you drag over a whole batch of files at once. So to make sure that the index numbers appear correctly for your files, what you need to do is start off first of all with an empty SD card. So delete any existing files and make sure that there's also not any hidden system files or folders or anything like that, because they will also be indexed by the audio module. So a completely empty chip, and then you can either save files to it individually in the order in which you want to index them, or you can prepare all your audio files in a directory somewhere on your computer using sequential numbers, and then drag them over all at once, and your operating system will, generally speaking, take care of the fact that they'll be copied over in the correct order. That's going to give you predictable index numbers so that you can call the correct sound effects from code or from the appropriate trigger pin. But if you later rename any of those files or delete and add new ones, you might find that the numbering system becomes messed up over time. And if that happens, there's a tool that's really useful called DriveSort. So you can download DriveSort for free from this website. The latest version is version 1.242, and you can read more about it here and download it by clicking the link at the bottom. Now, it's a nice, small, simple application that looks like this. It really only has one screen to the user interface. So to use it, the first thing you need to do is select the disk that you want to sort. So this is going to be the USB connection to the SD card or to the flash memory device that contains your audio files. And when you double click to open it, will show you the files that are currently stored on that device in the order as they appear in the file allocation table. Now, as you see in this example here, that doesn't match the file numbering. So what you can do is to choose a basis on which you want to sort those files instead. You could sort them by size, by creation date, but most commonly you're going to want to sort them by the short name of the file. So if you click that as a basis and then go folder sort, you'll see it rearranges the files into the new order, and if you're happy with the order it's given it, you can then save those changes, which will physically reorder them in the file allocation table. And having sorted the files on the drive, you can now access them through the index number you'd expect. So if you set the audio module into momentary trigger mode by setting the dip switches as follows,
You can then connect push buttons to the 8 I/O pins on this side of the board. The other side of each of those push buttons is connected to ground, and when you ground each of these pins, the corresponding indexed audio file is played. So pressing this button will play the first index file, then the second, third, fourth, fifth, sixth, seventh and eighth. And if you're controlling the module through serial commands sent from an Arduino, you might want to check out this library, which is available on GitHub, and that makes it really easy to access all the functions of the board. To play a particular numbered audio file, you simply initialize an instance of the player, and then you call the play specified method, passing in the index number of the audio file you want to play. And because we're not using physical buttons anymore, that number is not constrained to just being a value between 1 and 8. You can pass any index number up to 65,535 different files in the index table. And of course there are still many other audio boards on top of the ones I've described in this video. And some of those that I've used in the past include this Adafruit soundboard, which is based on the VS1000D chip. I've also used these two boards, so both ones in the form of a shield and a breakout board that use the VS1053. Now these are great if you want to record audio as well as play it back. And I've also used this is the WAV trigger by Robert Sonics, and this is based on a completely different architecture again. This uses a custom ARM chip. And those are all great boards in their own right, but if I were to recommend an audio board right now for you to integrate in your small electronics projects, I would have to say I would recommend either the 5W or the 8F if you have moderate audio requirements, or if you want to go for something much louder, much bigger, go for the upgraded versions that have the 20-watt amplifier. And you can choose whether you want to use the flash or the SD card versions. Based on my very limited test, I would say the SD card version is more flexible, it's actually a little bit better performing, and they cost exactly the same amount. So for all that additional storage, I would say it's probably worth it. Now, as always, what I'll do is I will copy the wiring diagrams and any code that I've used in this demonstration, and I'll put a link to that in the description below. So if you have any comments or questions or issues following those, do please let me know, and I will do my best to try and answer them, because there's a lot of misinformation on the internet about these different boards, but used correctly they really are really impressive, and they are not expensive at all to use, and it just adds another dimension to your projects. Other than that, I just want to say thank you all very much for watching. Thank you especially to my Patreon supporters who enable me to create these tutorial videos each month. I really appreciate your support, and I look forward to seeing you next time. Okay, cheers, bye.